All right, pre-calculus, we're going to talk about polynomial functions. Basically, some of the things we've already been doing have been polynomials, but this will just kind of open the door up a little bit more. And let's just start with some terms here. So the degree, again, is just going to be the highest exponent that you see in the function. So, I mean, whenever you're dealing with linear functions, you're really dealing with first degree because they're just like x to the first power, mx plus b. And then quadratic functions have x squared, so they are second degree. But just a few of the first 3 or 4 here. If the degree is 0, that just means it's going to have no variable in it. Okay, so it's just going to be like x to the 0 power. So this one is actually just like a constant is what it's called, because it's just a number. Like, for example, it could be y equals 2 or something, right? There's no x in there. It's 2x to the 0 power. And the parent function, since it's a constant function, just a constant value, is just going to be a horizontal line. Okay, but that would be considered a polynomial. Next, I said when the degree is 1, we call those linear functions. The parent function would just be like y equals x. Okay, or it could, you could do transformations. You could have transformations of that, y equals mx plus b, which we've seen a ton of in algebra and everything. But without any transformations, the parent function just y equals x, of course, is a linear function. That one would have a slope of 1, a y-intercept of 0. When we get to second degree function, those again, of course, are called quadratics. And that's usually the next big group of functions that gets discussed in Algebra 1 and in Algebra 2 as well. The parent function, of course, is y equals x squared. And again, you have transformations all over. We saw that in the previous section, actually. When you shift left, right, you have vertical stretching, all that stuff. But you get this basic U-shaped, a parabola is the technical term there. Third degree functions are cubic functions. Okay, and the parent function is y equals x cubed. Okay, we saw that earlier in different sections as well. It's going to have a basic shape kind of coming up through the origin like that. One end goes up to infinity while the other goes down to negative infinity. And then the next one, if we could just continue this, quartic, fourth degrees are called quartic, like a quarter. Parent function again is y equals x to the fourth. And of course it has all the transformations as well. And the thing with this, it kind of looks very similar to the quadratic. Okay, it might just be a little bit steeper. It's going to grow faster. It's x to the fourth power instead of x to the second. But a lot of similarities with the quadratics. Okay, and of course this goes on and on and on. So basically the idea with a polynomial is you're just going to have the sum or difference of a bunch of terms with x's to a power. Okay, you're not going to have any x's in the denominator. Those would be rational functions, totally different group of functions. No trig functions in here. So, just a sample polynomial, just a random example could be something like y equals 6x to the fourth minus 3x squared plus 8x minus 6 or something. Just something like that where you have x's to whole number powers and to positive powers. Okay, so anything like that would be considered a polynomial. They have some cool properties to them. They're very smooth graphs. They're continuous over all real numbers. Okay, so you don't have to worry about asymptotes or holes. So they're kind of one of the simpler things to study, and that's why in calculus there's a lot of properties for them as well. So in pre-calculus we're just going to kind of dig into a little bit more of their actual properties. How can we tell what the ends are going to? There's a thing called end behavior. We're going to find zeros and all that good stuff. All right, so let's consider, let's just do a quick sketch for each of these here. These are going to be some of the basics, which we saw on the previous page, but I want to get a nice pattern to jump out to you guys. So let's throw some xy axes on here. So again, we know y equals x. It has a positive slope through the origin. X squared, quadratic opening up. X cubed, x to the fourth. Okay, and then with these negative x, so it would just have a negative slope. Negative x squared would be the parabola opening downward. negative x cubed. So these are all just basically reflections of the graph right above it, okay, reflected over the x-axis. And what I want you guys to recognize here is that on the end behavior, that's kind of what I'm leading towards in this topic here. On the ends, okay, if you look at all the top row, every single one of these on the right side, okay, on the right end, the y values are increasing. Okay, and the way we're going to write that, okay, it's kind of a little complicated or a little fancy looking at first, but we say as x goes to infinity, okay, and that's just a way of saying on the right, okay, over here, right side of the graph, right, think of a number line. The x values are getting bigger and bigger, okay. On all four of these, the y values are also going to infinity, okay, but if you look at the graphs that had the negative multiplier out front, look at the right side only for now. If we focus on the right end, okay, for all of these, as x goes to infinity, okay, again, as we go to the right, okay, on the graph, the right side of the graph, all of these have y values that are actually going down to negative infinity. They're just going to keep going down and down and down. They're never going to turn back up, okay. There's no horizontal asymptote or anything, or there's not going to be another what we call turning point on the ends, okay? And what I want you to focus on is the ones with positive coefficients, okay, like this entire top row, the positive leading coefficients, what we're going to call it, right? That's a positive 1, positive 1, positive. As long as it's any positive number, the right end is going to go up. And the ones down here all have a negative leading coefficient, so the right ends always go downward. Okay, so that's going to be part one to determining what these graphs are doing. So that tells us about the right side of the graph, right? As x goes to infinity, we're going to know what the y values are doing just by looking at that leading coefficient. Now we still need to know what's going on the left side of these graphs as well. Okay, so to determine the left end behavior, what you're going to do is first off figure out the right end behavior, okay, like we just talked about using the leading coefficient, and then you need to take a look at the degree. Okay, if you take a look, let's separate these this way. Okay, take a look at the ones that have an even degree, okay, the y equals x and y equals negative x. Can you see how both ends go opposite directions? Okay, think of a linear function, right? One end's going to go up, one's going to go down. The x cubed, one end goes up, one end goes down. The even degree functions, though, your x squareds and your x to the fourths, both ends go the same direction, right? And I always just think like a parabola, x squared. Both ends are going to go up, or both ends are going to go down. Okay, that pattern is going to exist no matter how high the degree is. Okay, if the degree is any even number, both ends will go the same direction. And if the degree is an odd number, both ends will go opposite direction. Okay, so let's get a process here to determine this end behavior, then we'll do an example. So to determine the end behavior, first step, very first thing we're going to do, we're going to look at the leading coefficient before we do anything. If the leading coefficient is positive, the graph rises on the right. Okay, so you're going to know what the graph is doing on the right side just by looking at the equation. If it's a positive leading coefficient, it's going to go up to the right. If the leading coefficient is negative, the graph falls to the right. Okay, so step one is figure out what's going on the right side of the graph, just like when we looked at the examples on the last page. That'll tell you what's happening on the right. Now on the left side of the graph, we look and say, all right, if the degree is even, we know both ends do the same thing. Okay, so we'll do step one. We'll say, all right, what's the right side doing? If the degree is even, I know the left side's doing the same thing. Okay, if the degree is odd, both ends go opposite direction. Okay, so what this is doing, This is giving us a way to determine the end behavior without even having to graph anything. Okay, let's say it's a no calculator question. You're sitting there on the SAT. You want to know the end behavior. All they give you is an equation. You have no idea what the graph looks like. You can use this process to determine the end behavior. Okay, so let's walk through an example and kind of do it and see what happens. All right, so here's a function. Y equals negative 3x to the fifth plus 2x squared plus 6x minus 2. Okay, and let's do this end behavior first. That was the first thing we were talking about. So let's walk through step by step what we need to be looking for. Okay, so with end behavior, you need to make sure it's in standard form, which means the exponents are written decreasing. So I have the biggest exponent written first. Okay, that's going to be our leading coefficient right here. That negative 3 is the leading coefficient. Okay, since it is negative, that tells me, I'm just going to put a little sketch going here. That tells me since it's negative, I know this graph will be going down to the right. So one piece of the end behavior is going to be as x goes to infinity. Okay, that just means to the right. We know that y is going to negative infinity. Okay, just because we had a negative leading coefficient. Okay, and now the question becomes what's going on the other side? Well, since the degree is odd, I know the other side must be doing the opposite direction. So as x goes to negative infinity, right, that just means left, right? Think of the x-axis. Left is as x goes to negative infinity. I know in this case the y's are going up because it's an odd degree, so it has to be the opposite direction. Okay, so I could determine all of that end behavior stuff without even graphing the function. I know what's going on in the ends. Now there's some stuff going on in the middle. Okay, there's going to be most likely some zeros where we cross the x-axis and all that good stuff. In order to get those things, we either need to be able to factor the expression, which isn't always possible. So sometimes you're just required to graph it. Okay, a couple other things though. How many real zeros are there? What is the approximate value of the real zeros? Any max and mins? Okay, to do this stuff, we're going to need a graph. Okay, so let me go to the next page. This is in Desmos. Here's our function. Okay, we can verify what we said about the end behavior. See, the right end is going down to negative infinity. The left end is going up to positive infinity. But now we can see that there are 3 real zeros. Okay, real zeros are where you cross the x-axis. Okay, this has 3 of them. Now, we're going to notice once we start finding zeros down the road, whatever the degree is, that's going to be the total number of zeros. Okay, so in this example, there's going to be 5 total zeros. The graph only shows 3 real. Okay, so 3 real zeros. That means that there are 2 imaginary. And we'll get into that a little bit later in the chapter, how to find those. Okay, you can't find them from the graph because you don't see them on the graph. Okay, but we do know there are 5 total. 3 of them are real. We can use Desmos to get their approximate values. Okay, again, if things are factorable, you can get them algebraically, and we'll see some of that, but a lot of times they're not, and you just need to use your graphing calculator or Desmos to get the values. All right, and you can see the values. There's also minimums and maximums on here, which you can get from your calculator or Desmos here. These are called relative or local minimum and maximums this time. And the difference is, so like for example, this point right here, okay, it reaches a minimum right there, but that's not the lowest the graph ever gets, right? We have all these y values here as this graph continues down. That will get lower. So this point, instead of being the absolute minimum, we call a local minimum or a relative minimum because it's lower than the points near it. Okay, similarly with this guy here, it's not the highest this graph ever gets, right? This graph actually goes to infinity, this function. So that point, that y value of 3.249, that's a local maximum, okay? And then you can also give the x value of where it occurs. All right, so here's another example that you can walk through. Let's do the end behavior just as an example for one more practice here. So I'm looking again, the first term, the one that has the highest exponent. Okay, it's not always written first, but it should be, but it's not. In this case it is though. So I'm looking, the leading coefficient on that is positive. So that's telling me as x is going to infinity, since it's a positive coefficient, I know y must be going up to infinity. Okay, again on the graph I know the right end's going up. And then I know since the degree is an odd number, an even number, that means the left end is going to be doing the same as the right end. Right? Any even degree function has the same end behavior. So on the left side of the graph, right, as x goes to negative infinity, the y value is also going up. Okay, for everything else, the total number of zeros, again, that's going to just be whatever the degree is. For how many of them are real, we would have to look at the graph, okay, which I'm not going to do right now, but we could graph that and find it. We could find the real zeros and the max and min from the graph. Okay, the domain, cool thing about these, domain is all real numbers. Okay, for polynomials, remember they don't have any asymptotes or holes. So they are nice and smooth and continuous. Okay, and then for the range, we would have to determine where the minimum is. There's going to be a minimum somewhere since both ends go up to infinity. There's going to be some minimum value to infinity, and we'd actually include the minimum. So I don't know what that exact value is, but whichever part is the lowest on the graph, that would be the minimum for the range. All right, so how do we find some of these zeros? Let's say we need to find zeros. We don't want to do it graphically, or we can't do it graphically. Let's review some factoring methods. Let's just say, for example, these are like equals 0 or whatnot, or they were a y equals there, and we're trying to find the zeros. So just a real quick recap from some algebra techniques. Factoring things like this, x squared plus 6x plus 8. This is a nice quadratic trinomial. So I'm going to look for factors of 8 that add up to 6. Okay, so of course those numbers are 4 and 2. So this thing would factor into x plus 4 times x plus 2. And then we could set each factor equal to 0 using the zero product property, and we could get the two zeros that way. Okay. Similarly, part B, again, let's just pretend like this was being used to solve an equation equals 0. You can just factor things, or you can use factoring to solve equations. So let's just say that we're finding 0. So let's make them equal 0. This one step first, right? Notice each term has a common factor of x, so we want to factor that out first. Okay, and when we divide the x out, or factor the x out, we're left with this. And then the x squared plus 6x plus 8 is the same as the problem we did first, so it's factorable as well. Okay, so what that ends up getting us, if we set it equal to 0, so don't forget about this guy right here. X could equal 0, x could equal -4, or x could equal -2. Okay, so that one did have 3 solutions, right? It was a third degree. So again, you're gonna get 3 answers. Sometimes they repeat. Okay, and we'll see some of that. But that's a quick review there. Now, same thing if we're solving by factoring. If there's an a value other than 1, there's a couple ways. You can obviously go right to quadratic formula if you don't want to mess with this. But the method we kind of used was to multiply the a times c to get 12. And then what I want to do is split this 7x up in a way that it uses factors of 12, okay, that add up to 7. So we're going to do like 3 and 4. Okay, 3 times 4 is 12, and they also add up to 7. So I'm going to do 2x squared. I'm going to rewrite the 7x as plus 4x plus 3x. Okay, so all I did was rewrite this with 4 terms. And then it lets us use this method of grouping, which we do in algebra, where we're going to say, okay, what do we have in common with the 2x squared and the 4x? So they share a 2x as a greatest common factor, and we would be left with x plus 2. Okay, and then the 3x plus 6 common factor is 3, and the leftover would be x plus 2. And then this is going to work nice because we can see they both have this x plus 2 now. So you can bring that out front as a common factor. Okay, and the leftover stuff is 2x plus 3. Okay, and then we could set those each equal to 0 and get our final solutions of x equals -2. Okay, and setting the other one equal to 0. When you subtract the 3 and then divide by 2, you get -3/2. Okay, so again, we used factoring to solve equations, okay? And you can do that with some polynomials, okay? These are polynomials. As the degrees get higher, as your third degree, fourth degree, they definitely get a little more involved, okay? But some of these methods definitely still apply. You know, if I were to have given you these zeros, would you be able to come up with the function? And we should be able to. So once you know the zero, like when you know x equals -4 is a zero, you should know that x plus 4 is a factor that would get it. Okay, and you can do that. Okay, one other method, we actually saw this in part C, it kind of came back to it, but using this grouping method. So this problem here, this is not a quadratic, right? This is actually a third degree, this is a cubic function. And sometimes factoring works using grouping, okay? And generally, you want to try it when you have 4 terms, and you notice there's not a common factor across the board, okay? Not all 4 terms have something, but the first 2 do. They both share the greatest common factor of x squared. Okay, so if we factor an x squared out, we would be left with a 5x minus 8. Okay, then there's a minus sign in the middle. Now with the 20x and the 32, their greatest common factor is a 4, and we would be left with a 5x. Now just keep in mind I need to get back to a plus 32, so it would need to be a minus 8 there, okay, because we got the minus before the 4. And this is exactly what we hoped would happen. When you do grouping, you want to get these terms to be equal so that you'll now have a common factor, right? So we have a 5x minus 8 in common. The leftover stuff is x squared minus 4. Okay, and then we can still factor. Remember the x squared minus 4, that's the difference of perfect squares of x plus 2x minus 2. Okay, so that would be factored all the way down. Now again, this might have an equal 0 or a y equals in front of it, and we could find the zeros. I just want to show the factoring method of grouping just as a nice little refresher. Problems, each 0. Okay, here's another example of grouping if you want to pause and try that one out and take a peek just to practice the grouping method a little bit more. That's there. Previous one and multiply them out. Okay, and then finally one other thing, can we find the function if I give you the zeros? Okay, so kind of working backwards so let's take a look here. So find a polynomial with zeros at x equals 0, x equals -2, and x equals 1. Okay, so that means if those are the zeros, that means that the factors for x equals 0 just means there's a factor of x. Okay, for x equals -2, there would have to have been an x plus 2, right? Because setting that equal to 0 would get you the -2 answer. And for x equals 1, it means that x minus 1 must be a factor. Okay, now we do probably want to do this in standard form. Technically, you could just leave it like this. This would be, factored out form. But we should probably multiply it out. So to get it to standard form, we're just going to multiply. So let's multiply. Let's do these two first. So I'm just going to distribute the x to become x squared plus 2x. And now that still needs to get multiplied by the x minus 1. So if we do that, right, we distribute our FOIL method kind of thing here. X cubed, x squared times minus 1 is minus x squared. Plus 2x times x is plus 2x squared. And then plus 2x times minus 1 is minus 2x. And of course we can combine the middle terms to end up with a function of something like that, okay? And you can always verify these, graph this thing, and make sure that it actually goes through the zeros that it's supposed to go through. Okay, so this is just one example. You could actually multiply this by any constant whole number as well and get higher multiples of it, and it would still go through the zeros. It just would be like vertically stretched or whatnot. But this would be an example that goes through the 3 zeros. Okay, and one last little thing here. There's this idea of, for example, let's say we had a function that looked like this. Okay, so y equals x plus 6 all squared and then x minus 3. And what we want to just do is just state the zeros. Okay, so we're not actually going to want to multiply this out. We're going to just state the zeros. And the thing I want to mention is their multiplicity and what that means real quickly. So basically what ends up happening, the x plus 6 squared can really be thought of as x plus 6 times x plus 6. Okay, and the point is that this thing is really a third degree function. Okay, because the x plus 6 is, there's two factors of that. So what that means is that the zeros are going to be x equals negative 6 and x equals 3. But since there were two factors of the x plus 6, what we say it has a multiplicity of 2. Okay, and what it means is that the graph will not go all the way through negative 6, but it will actually just kind of touch the axis there. So let me do a quick sketch of this and see what's going on. Okay, so just looking at decimals real quick to sketch a graph and just visualize this last thing. So I can see, again, it's going to have zeros at negative 6, right there, and also at positive 3. Okay, but whenever there's an even multiplicity, the graph just touches, oops, I don't want to use black, the graph just touches that point and doesn't cross through. But the positive 3 had a multiplicity of 1. The graph will actually go through there and cross from negative to positive. Okay, so I just want to point out that term of multiplicity. This is still a real zero, and it just kind of appears like there's only two real zeros here. But since the negative 6 had occurred twice, it kind of counts as two real zeros, because again, we would know we need 3 because it is a third degree function. Okay, so that's all multiplicity really means. And you can tell by looking at the graph, as if the graph crosses through it, it would be an odd multiplicity. But if the graph just kind of comes up and just kisses the graph there, barely touches and goes back down, then it's going to be an even degree multiplicity.